Shall I start?
Yep. Yep.
Okay. Hello, everyone. Sorry I can't be there at the Beam Day. Unfortunately, I had some complications due to my recent bronchitis, but hope that my presentation will be informative enough. So please tell me immediately if there is any connection problem. Otherwise, I'll proceed. So this is a kind of little technical talk about post-quantum signatures for the Beam chain. This is a joint work with Justin, with Mike Kodinov and Benedict Wagner. Benedict also from the cryptography team. So I'll try to make it less technical, but still interesting enough for participants. So basically how we started, we needed a simple signature scheme, which would be easy to implement, to test, to analyze. We need the minimum number of hardness assumptions, I mean cryptographic hardness assumptions. I mean the assumptions that are necessary to prove the security of the scheme. We need the scheme to be resistant to quantum attack. The signature should be of reasonably small size. Well, we know that for post-quantum signatures, they cannot be like super small, but still reasonably small. We need that they are fast to sign and to verify, because all this is under the pressure of slot timing. And we need those signatures to be aggregation friendly, because we don't plan to have them all in the blockchain, but we have to have some aggregation of the signatures, because there are like many validators per slot, and having all the signatures in the plain text is just would consume too much bandwidth. And to these requirements, we have come up with a simple solution. Shortly, it's called XMSS. It's a hash-based signature scheme. And its advantage that it uses just a collision and preimage resistant hash function. Nothing more, as long as this hash function is resistant to collision preimage attacks and to quantum attacks as well, means that the hash is not based on any, for example, elliptic curve machinery, then this scheme is plausibly post-quantum secure. It's also of reasonably small size. It's between 2 and 3 kilobytes, depending on the parameters. We have some trade-off between verification time and signature size. It's reasonably fast and sign to verify, really fast. It just takes milliseconds to sign and to verify. And it's aggregation friendly. By aggregation, I mean that it doesn't have any internal algebraic structure to make it aggregation friendly, but we can aggregate it to prove the knowledge of sufficient number of signatures. And to give you some concrete numbers, in order to prove the knowledge of 1,000 signatures, it's equivalent to prove just little more than 10,000 Poseidon hashes. And we know that the signatures, 10,000 Poseidon hashes, can be proven in reasonably small time. This will be covered in the next talks. And now I will try to explain how the signatures work. So I'll start with a toy example. In this toy example, I first explained how keys are generated. So in order to generate a public key, we create 5 secret inputs. So this 5 is just the toy example number, and in practice it will be a little bigger. So here the ones are S1, S2, S3, S4, S5. They are at row 4. These are also called chain beginnings. And then we hash each of those 4 times, like 1, 2, 3, 4, reaching level 0. These form a chain. And then the resultant hash outputs, we hash them again with like little bigger hash, and we get a public key. And that's it. So that's the key generation. Now how to sign and what can be signed in this toy example scheme. In this toy example scheme, we sign messages, and these messages are 5 tuples, meaning like there are 5 numbers, and each number are between 0 and 4 integers. But not all combinations are possible. Not all 5 to the 5 combinations are possible, but only those whose sum is 8. What that means? Here is an example. For example, we can sign a message consisting of 5 numbers, 1, 3, 2, 0, 2. It's easy to see that they sum to 8. And then, so this 1, 3, 2, 0, 2, they give us the positions in this chain. Means like here at level 1, here at level 3, here at level 2, at level 0, at level 2. The actual signature is the array of values, not the positions, but of values. So this hash outputs. Again, like since we have 5 so-called chains, the signature is composed of 5 hash values. With this scheme, we can sign several messages. For example, we can also sign the message which consists of, again, 5 numbers, but now they are 40004, like here. And then again, I would have this 5 orange balls are signature values. They form a signature. In order to verify this signature, it's enough to hash all the chains till their end. And it's easy to see that since the sum of positions is 8, then for every message, we have to apply the hash exactly 8 times. So now then we get chain ends, and then we hash them again and check if they match the public key. It's also easy to see that from any actual signature, you cannot modify it to get a signature for another message whose sum of positions is also 8, because in one of chain, you would have to kind of step back in the hash chain to find the preimage to the hash, which is impossible. So in this TOE example, since we have only 5 chains and each chain has 5 entries, we can only sign 320 messages with the sum requirement of 8. But if we modify this a little bit, and this is actually very close to the construction we have, then for 64 chains of length 8, and if we require that the sum of positions is 76, then we can sign almost exactly 2 to the 128 messages. Well, little more actually, because we need this little bigger number for security proofs, but around that. And this actually gives us 128 bits of security. So the actual scheme will be very close to this. We'll have 64 chains, meaning that the actual signature will be will consist of 64 values. So that was a one-time signature. And for how to convert it to multiple time signature, that's actually very easy, because in this particular Beam chain application, we know that each validator signs for a particular slot, and all the signatures are enumerated. For one slot, there can be only one signature, and then it's relatively easy to have multiple signatures. From one, what we do, we actually just create a one-time signature for every slot. If we have like 2 to the 32 or 2 to the 24 slots, we create appropriate number of one-time signature, and then we make a public key out of them by just making up a Merkle tree out of all them. This means that in order to verify a signature, a one-time signature, it's enough to verify it up until the leaf in the tree, and then we need another Merkle proof part to verify it up to the very end of the public key. And this part can actually be amortized in practice. So this is done, and how actual signatures are generated. So suppose a validator wants to sign a block B at some slot number V, then it hashes it, B and V, and get positions from W1 to W64, positions on this chain structure, which we also call a hypercube. And these positions, they determine which values have to be provided. So how validator makes them up, it recalls basically how the chain beginnings were generated. It iterates up to the orange positions, and it outputs them as a signature. So 64 values, 64 chain values are signature, well, plus the Merkle tree part up above. In order to verify the signature, again, you just have to compute the hash. You have to compute the hash chains up until the ends, and then to the Merkle root. In order to do this, you just have to compute about 136 Poseidon hashes, and that's it. Well, this number 136, it varies a little bit if you need many more slots, but if you just double the number of slots, number of hashes as in the Merkle tree proof increased by just 1. And in order to aggregate this, in order to prove the existence of signature, you just put all the signature verification process into the circuit. Basically, what you do is to prove the existence of a signature, you hash block and slot number, and you get the positions, and then the signature exists if there exists chain entries from chain 1 to chain 64, such that if you hash them till the end appropriate number of times, and this number of times is determined by the hash of block and slot number, and then there exists the Merkle proof till the end, then that means that the signature exists. And that's it, basically. The theoretical part behind these constructions is in 2 papers that I just published on ePrint on these links. They don't contain the full scheme that will be actually used. It will be in the final report, which is just to be finalized. We kind of wrapping up with some security proofs and some kind of parameters. Based on this, it will be published very soon. Based on this, we'll write a spec, which will be good enough to make a code out of this. That's it. Thank you. Are there questions?
Thank you. Thank you, Nicholas. Any questions? I'll relay them.
What were the other choices in the designs, and why did we choose this one as opposed to?
So the question is, what were the choices when designing post-quantum signatures, and why was the hash-based construction selected?
Right. So we, of course, are aware of a number of post-quantum constructions, particularly lattice-based. So what we end up we're afraid of is that while the analysis of lattice-based schemes still continues, there are a lot of discussions about security of this scheme, how to interpret the security. Also, what we do like is that we really have smallest number of hardness assumptions, particularly just the security of a hash function. Since we already have to have a secure hash function, then it means that we can get a secure signature scheme without any additional assumption. So if we use a lattice-based scheme, that we need to assume something lattice specific as a hardness assumption. If we just use a secure hash, we don't need anything else. And also, the hash-based signature scheme is much easier to verify in circuits, because it's kind of the domain is better suited to the domain where proof systems are built. Well, of course, lattice schemes are still competitive, and we think that it's a viable alternative, but simplicity of this scheme and its minimal requirements and the ease of implementation, I think, give it a little advantage. That's it.
How often do you think we should rotate the public keys, and how big are they to store?
How often should we rotate the public keys, and how big are they?
Yeah, so for multiple signatures, the number of public key determines how big the Merkle tree is. So I think we can support up to 2 to the 24 slots is supported easily. I think we can even support 2 to the 32 slots, which should be sufficient for all the practical purposes. Well, this will make the key generation a little more expensive, maybe several days, because you have to basically calculate all these hashes. It means that 2 to the 32 times, you have to calculate all these, 500 chains, 500 hash calls or something. So in total, hundreds of billion hashes, which is feasible, but takes some hours. But overall, I think it's possible. So for of course, there can be some aggressive variants where you have really small tree and you rotate the keys pretty often, but I think we can avoid it. So maybe we should aim for bigger trees, but to maybe cache this part, the upper part, in some smart ways to reuse it in proofs and in other parts, because actually the outer part is not confidential at all, in contrast to these blue things below. So any number between 2 to the 24 and 2 to the 32, which is required, I think we can support.
So one of the strategies that we've taken recently is to introduce two different concepts. There's the concept of a maximum lifetime, which is, for example, 2 to the 32 slots, which would be a century, even if we have 1 second slots. And then there's the actual lifetime that you would generate, practically speaking, as a validator. And here, what we would recommend to the clients is maybe only generate 8 years of lifetime, which is 2 to the 24 keys. And that would take about 3 hours on your laptop. But yeah, if you want to generate 100 years of lifetime, then that's up to you to just spend more time on the key generation.
Yeah, small technical question is just, so when you hash the block and the slot, how do you make sure that that maps to one of these particular arrays that you need? I didn't know, I missed that part.
Yeah, great question. So the question is, when you're hashing the message and the slot, how do you make sure that you have the target sum?
Right. So what we actually have here, so we hash the block and slot into some kind of long string. Then we convert this long string into an integer. And this integer, simply saying, we take it modulo the number of possible output positions. So here, like how many positions so that they sum to 76 onto 64 chains exist. There are about 2 to the 128, 2 to the 135 or something. So we know this number. This is just a combinatorial thing. So we take hash modulo 2 to the something, basically. And then we take, based on the result, we figure out in which position we are by kind of applying, again, recursively combinatorial things. So it's basically the question how to generate all the
There's some grinding, Dmitry, right? It's
Sorry?
the grinding allows us to hit the target sum.
Yes and no. So we can do this with grinding. Grinding allows us to use like target sum, which is a little smaller than needed. But I think it's to explain this, we don't have to talk about grinding. So here we just can map a big integer into the position. So it's the question of enumerating all arrays of integers whose sum is equal to some constant. And this is combinatorial thing, how to generate all possible enumerations. And in our second paper, there is exact algorithm that does that. It's kind of a simple combinatorial thing, a few divisions, modular reductions, and that's it. There is indeed little grinding over it, but I think it's not required to explain how we do mapping.
Okay, one last question.
Why do you need to generate all the positions? Why not just the one that represents your integer? I didn't understand.
No, I meant that in order to convert a big integer into the positions, we need the algorithm that maps one-to-one. And this algorithm is sort of similar to the algorithm that generates all possible positions. The actual algorithm that maps is like, for example, if you have like a big integer, how do you write it base 10 or base 16 or base 5? You do some modular reductions, subtractions, divisions, modular reductions, subtractions, divisions. Here it's about the same, just a little more sophisticated because of the structure of this hypercube, but principle is about the same.
Thank you so much, Dmitry.
Thank you, Justin.
Next up, we have Emil, who will talk about recursive aggregation.